So, welcome back. We have just finished the study of the plan space planning algorithm, and just to recap, we start by creating an empty plan of two actions A 0 and A infinity. A 0 produces the predicates of the start action, and if we look at this particular example, the predicates are these. So, these must be the effects of the initial action A 0 when we start doing plan space planning. These actions are basically describing the diagram on the top, which says that A is on the table, C is on the table, B is on C, there is nothing on top of A and there is nothing on top of B, and the arm is empty. The last action A infinity will consume the goal predicates. The goal predicates are two in this case. One says that B is on the table and the other says that A is on B. We do not care about anything else. We do not care where C is and whether the arm is holding C or whether the C is somewhere else. Maybe it could be on A or maybe it could be on the table. It does not matter to us. So, this is a starting plan that we begin with. So, as you can see, the start predicates are the effects of the start action A 0, and the goal predicates have been consumed by or will be consumed by the last action A infinity. The plan, as we said before, is A 0 A infinity, an ordering link which we are not showing here, just so that the diagram does not get cluttered up. Essentially, we will assume in the next few slides that unless shown explicitly, the actions which are higher up in the slide happen before actions which are lower down in the slide, which basically means that time is flowing like this from top to bottom. Any action which is higher happens first and any action which is lower happens later. Now, this empty plan A 0 A infinity stands for the set of all possible plans that you can construct in this thing. Now, it so turns out that this set is actually infinite. Why is this infinite? Because you can simply have a sequence of actions which go into a kind of an infinite loop, or if not in an infinite loop, in a small loop. So, for example, you as you can see, you have on B C in this start state. So, you can say unstack B from C, then you can change your mind and say stack B onto C, then you can again say unstack B from C, and again you can change your mind and say stack it onto C. So, we can have a sequence of plans that unstack B from C, then stack it back, nothing is stopping us from doing that, then again unstack B from C and again stack it back, and so on. We can do this any number of times, and any plan which incorporates these four actions would still be a valid plan. Of course, it would not be an optimal plan, but it would still be a valid plan. So, in that sense, the space explored by plan space planning, even for this tiny problem that we are looking at, is infinite, whereas the space explored by state space planning, forward state space planning, backward state space planning, goal stack planning would have been finite essentially. So, that is one little bit of a difference between the two approaches. So, we add the first action. Remember that basically the planning algorithm is driven by removing flaws, and to start with we had two flaws in this thing. There were two open goals, and one of the ways of catering to an open goal was to add an action. So, clearly, as we have seen by now, that to cater to this open goal on A B, the action that is relevant is stack A on B. So, we add this action to the plan essentially. So, what does that mean? That we add this action stack A B into the first set, which is a set of actions. We establish a causal link from A B to on A B to on A B, and we add that as a explicit element in the set of causal links. And finally, what is not shown here is that we add a ordering link. We should add a link saying that this action happens before this action, but we will not show it because the slide would become more cluttered. We will show it towards the very end. Now, another way of solving an open goal is to find an existing action. Now, you can see here that clear B is true in the start state, which means it is produced by the first action, and that is what you needed. So, you can just go ahead and establish a causal link between this, and the causal link is represented by this arrow. It would be added to the plan by saying that this triple A 0 produces clear B and stack A B consumes clear B. So, we add this to the set which we call as C essentially. So, we add it, and as we have been saying, we will also add an ordering link between these two actions. The other, so what we saw here was one open goal. So, at this moment you can see that this open goal has been taken care of, this open goal has been taken care of, this one still remains and this one still remains. So, let us assume that our algorithm is going to address this open goal holding A, and because to execute the action stack A on B, we need holding A to be true. So, we need a causal link for holding A, and that will be provided to us by pickup A. We could have chosen like in goal stack planning either pickup A, or we could have chosen unstack A from something, but let us say that somehow we have managed to choose this action pickup A, inserted it into the plan, that means added it to the set of actions, establish this causal link here, establish the ordering link which we have not shown, and so on. And it steps that I will skip for each of these open goals, we can establish links from the start action because they are true in the start state. So, we have now addressed many open goals, but we are left with one which is to be addressed still, and you can see that says that B should be on table, and we know that the action which will do that is to put down B. So, we add that action to the plan, add the corresponding causal link, add the corresponding ordering link, and then we find that there is still one open goal left in the plan, which is holding B. Holding B, like holding A that we saw earlier, could have been achieved either by unstacking B from something or by picking up B from the table. And let us say somehow we manage to pick the right action in this case. Maybe we can look at the effects of the start state or maintain that somewhere to guide search in a way, so that we only select meaningful actions. But even if we can't do that, we can always backtrack and try something else. So, the action that we have added now is unstack B from C, and the preconditions for this action, which are arm empty, on BC, clear B, are all true in the start state, and at this point we have solved all open goals. There are no more open goals in the plan. What about threats? So, let us look at what is happening with threats. You can see that this action stack A B is a threat because there is a causal link between clear B and clear B here, and this is doing not clear B. So, clearly this action is a threat to that causal link. So, at least there is one threat, but it so turns out that in fact there are 3 threats, all of them are to do with arm empty. It is not surprising that this is the case, because the problem that we have defined, the domain we are working in, the strips domain, it works with a one armed robot, and this one armed robot can only handle one thing at a time. So, the moment it picks up something, its arm is no longer empty, and if some other action wanted arm to be empty, then clearly there would be a threat somewhere, and we can see that there are 3 threats here in this case. The first one we have already identified as we let us call it T 1, but there is another threat which says that pickup A also produces not arm empty, and unstack B C wanted to consume arm empty. So, pickup A is a threat for this link, which is this link, right. And likewise, unstack B C is producing not arm empty, and that arm empty would have been consumed by pickup A. So, we have this third threat, which is T 3 essentially. So, we have 3 threats and we can remove them one by one. Now, in this example there are no variables, we have not said unstack B from something. We could have said that, but it would not have affected our plan. We just took the liberty of choosing the action unstack B from C, because we could see that on B C was true in the start state. So, we can remove these threats one by one. So, here I have introduced the ordering links which we have found so far. When we added each of these 4 actions, we added some ordering links for those actions, and of course, there is a original ordering link which says that this must happen before this thing, which I have not again drawn here. So, these are the red colored links are the ordering links, the dotted links are the causal links, and these thick shaded these thick gray arrows, these are the threats to the causal links. So, there are 3 threats as we saw. The threat number 1 can be resolved by saying that unstack B C, which is this action, must happen before stack B on C. So, once it is unstack B C is done, that means it has consumed arm empty, and it is no longer bothered with about the fact that stack A B is going to it is consumed clear B, and it is no longer bothered about the fact that stack A B is going to destroy or clobber clear B. Likewise, we can add ordering link to say that unstack P C must happen before pickup A, so that this arm empty condition is not conflicting as it was in thread 2, and in a similar fashion by saying that put down B must happen before, this is a link that we are adding, pickup A, and then the third threat will also vanish. So, at this point we will see that there are no more threats in the plan, and we can kind of draw a neater version of this to say that this is what finally matters. There are other ordering constraints that we spoke about, but eventually what this produces is a plan which happens to have a linear structure, which says that the first action that you do is unstack B from C, the second action you do is put down B, the third action you do is pick up A, and the fourth action you do is stack A on to B. So, at the end of it you have stack A on B and you have B on the table, and this is the plan. Now, it is not surprising that it is a linear order, because as I have said that we are working in a domain in which there is a one arm robot, and this robot will do these 4 actions in a sequence one by one and produce the final goal, produce a plan which will achieve our goal. What if we had a 2-armed robot? So, for the same problem that we are trying to solve, let us say that the domain is allowing us to, or the domain has a robot which has got 2 arms. In the given domain, as it was in the strips domain, it was only possible to have a linear sequential plan of 4 time steps. What if we had a 2-armed robot which could do actions in parallel? So, now as you can see in the diagram, there are 2 arms, and how will that change the process? So, as you can imagine, for example, the 2 arms could so one arm could unstack B from C, while the other arm is picking up A. So, these 2 actions could be done parallel. So, maybe you can get a shorter plan in terms of the number of time steps. We call that as make span in terms of planning, and it is possible that these things may happen in parallel essentially. How long would the plan take to execute? So, that is a small exercise I would ask you to think about, and we will take it up in the next session. The real problem here is for you to modify the strips operators to cater to the domain in which there is a 2-armed robo. Now, in the original strips operators that we had actions like pick up, for example, A. Now, what is the meaning of pick up A in this world where the robot has 2 arms? We should be able to specify which arm is picking up A, and that needs to be now part of the modified domain description, and I will leave that as a small exercise for you. I will give you one suggestion now, but hopefully you will look for better suggestions and come back before the next lecture. In particular, what I would like to ask is, does your solution extend to multiple arms? So, let us take the 2-arm thing first, and here is another problem for which I will give you a solution a little bit later. This is a problem in which in the starting state there are 2 stacks, D is on A and C is on B, and you have 2 arms, arm 1 and arm 2, and the goal state is that you have to stack D onto C and C onto A essentially. So, as I said, modify the strips operators to work with arms 1 and arm 2, and also as an exercise show the plan that partial space plan space planning will produce at the end of it. So, the first thing you should be able to observe is that it is not necessary that the plan that is called as a solution plan has a sequence of actions. The very fact that we have introduced 2 arms into our domain allows for the possibility of parallel actions, and you should be able to observe how that would be possible in plan space planning. How would the planner give us a plan which could be executed in parallel wherever it can essentially. Let me give you one brute force or simple method, and this method says, now here you have this stack operation. There is something that I have not kind of emphasized during these talks on strips planning, is when you for example pick up an object from the table or unstack it from another object, that object X, let us say. So, at the moment when you pick up or unstack, one of the preconditions is that object must be clear. So, clear X must be true. So, should we delete clear X or should we let it be? The reason for letting it be would be that anyway after you have picked it up and after you have unstacked it, the only thing you can do is put it down or stack it onto something else, and then anyway it will become clear. So, why bother deleting clear X in pick up and unstack and then adding it again in put down or stack? So, at least for the single arm robot that did not make too much sense, and so let us begin with that. We may want to consider the possibility of our arm robot being very versatile, two arm robot being very versatile and being able to, for example, stack one block on another while holding the other block. So, then we have to be a bit careful about this clear predicate. In the simpler case, we assume that we had not deleted clear x. So, when we stack A onto B, for example, in this case, we do not have to add another effect which says clear A. So, because we have assumed that they are not deleted, we are not adding this here, but that would be an option essentially, but then you would have to modify pick up and unstack appropriately. So, working with this version where we are not deleting that clear thing, the simplest thing to do is to simply have two separate actions just with different names for the two arms and without going into too much creativity. Let us just assume that the action is called stack 1 and the other action is called stack 2 essentially. So, they are just different names. I could have given them any other names, after all there is what is in a name, Shakespeare said a rose by any other name would smell as sweet. So, from the planning perspective or from the computing perspective, an action by any other name would still do the same thing. But the simplest brute force approach is to just introduce two new actions. One is called stack 1 and the other is called stack 2, and the precondition we need to modify the predicates. So, that we have now holding 1 and this should be holding 2. So, holding 1 is a precondition for 1 and holding 2 is a precondition for the other, and likewise the arm which becomes empty is clearly specified. So, we are just treating this as a separate action. They are just two different actions. In some sense we are separating the world of arm 1 and arm 2, but what would happen if we had multiple arms? What if I give you a robot with 2 arms and 3 arms or 4 arms and things like that? Maybe you should look for an way of modifying the strips actions so that they can be extended easily to any number of arms essentially. The other thing that I would like you to think a little bit about is that if you wanted to allow the robot to become versatile, which means that it can, for example, with one arm it can pick up block A, on another arm it can pick up block B, and then while holding it, it can put A onto B without putting it down on the table. So, if you wanted to do that sort of a thing, where you could do things in parallel, or let me take you back to the example that we started with. Supposing in the first time step arm 1 unstacks B from C and arm 2 unstacks or picks up A from the table. Then is it possible for the two arms to in one time step achieve this goal of saying that B is been put down, but at the same time A is been stacked onto B? How would you think of modifying the planning operators to do that? So, I will leave you with this small exercise and we will ignore this simple solution that I have given, and in the next session we will see how to model versatile multi-arm robots essentially. If there are many robots, many arms in a robot, or maybe more than one robot with let us say 2 arms each, and if they are versatile in the sense that they can manipulate objects which are not on the table, then how would you model them? One place where this kind of a approach would be meaningful is if you are talking of a multi-agent scenarios. So, if it is not just one robot, that you have many robots and they have to coordinate and collaborate and then do things together, Then as an example, for example, if there is a table that you want to move from one corner of the room to another corner, then the two robots have to coordinate their actions in such a manner that both of them lift the table from either end, from the two ends simultaneously, and carry it and then put it down at the same time. So, it is just an exercise in trying to see how you can extend simple strips domains to more complex domains. We will do a little bit in the next session. So, see you then.